Well, hello. So we're continuing to look at convergence tests for series of positive terms. You may have already seen the video about the ratio test. The next test we're going to look at is the root test, a very similar sort of test. You can actually probably get along without the root test, but we're going to go over it because in cases where it works, it's really fast and slick and pretty easy to use. So the root test, similar to the ratio test, it's a test for series of positive terms. So let's let a sub k be an infinite series of positive terms. And now we're going to take a look at the following limit. We're going to take the nth root of a sub n, so the first root of a1, the square root of a2, the cube root of a3, etc. That gives us a sequence. And then take the limit of that expression as n goes to infinity. And again, we're going to get some number out. We'll assume the limit exists for now, call it rho. And as in the ratio test, we have similar conclusions. If the rho is greater than or equal to 0 and less than 1, that will tell us the series converges. If the rho is bigger than 1, and even could be infinity, then the series diverges. And if rho equals 1, or this limit in star does not exist, the root test tells us nothing, and so we have to go back and try something else. So this test works well with series whose terms involve exponential functions. So usually I recommend the ratio test if you have factorials, because taking nth roots of factorials can be difficult. But when you choose to use the root test, it might be useful to remember this limit we saw when we studied sequences and also when we looked at L'Hopital's rule. But a very important one that shows up now and then is that in general, the nth root of n as n goes to infinity turns out to be 1. And we'll be looking at this and some minor modifications of this that also often give us 1. So let's take a look at the series summation k goes from 0 to infinity. K plus 2 over 3 to the k to the 2k times 5k squared plus 1, all raised to the kth power. So with all these kth powers in the a sub k term, this is kind of an ideal series for the root test. So we're going to take a look then at the limit as k goes to infinity of a sub k to the 1 over k. And to get a sub k, as in the ratio test, you can just go up to the series, erase the summation, and what's left is the a sub k term. And we're taking its kth root, or raising it to the 1 over kth power, so we get that here. Now, that kth root, factors inside. So, for example, we can read this as the kth root of 3 to the k, which is 3, etc. So this 1 over k power factors into a 1 over k power on the k plus 2, on the 3 to the k, on the k to the 2k, etc. Remember, when you have an exponent of an exponential like this, you multiply the exponents together, and so we have the following result in the limit. So we're going to remember here that just as the limit as k goes to infinity of k to the 1 over k equals 1. I mentioned we see some various minor modifications. It turns out that if you add any constant to the k down here and still take the kth root, you're going to get 1. So that's why we've replaced this expression here by 1. And 3k, 3 to the k to the 1 over k power is 3. K to the 2k to the 1 over k power is k squared. And likewise, a 5k squared plus 1 down here. This is a pretty easy limit from Calc 1, just gives us 3/5. 3/5 is less than 1, so this series converges by the root test. Now, the root test usually works best on series, again, whose terms involve exponentials. The ratio test usually works better on series whose terms involve both exponentials and maybe factorials. Now, again, as we saw with the ratio test, for series of this form, where they look like summation of pk over qk, where pk and qk are both polynomials, you'll find that both the root test and ratio test fail for such series. In other words, the rho turns out to be 1. So series of this sort are going to be no information cases. you'll have to probably use a comparison test or maybe an integral test. Now, the root test can be thought of as really a test that compares a series to a geometric series. The same is true of the ratio test. Both of these tests are really just comparison to geometric series. We're going to see why that's the case for the root test here, because it really is a pretty easy argument. So let's take a quick look as to why these work. So suppose we have a series of positive terms, summation n equals 1 to infinity a sub n. We look at the limit of the nth root of a sub n, or a sub n to the 1 over n, get rho less than 1. So why does that imply convergence? Well, if rho is less than 1, then we can find a number r that is between rho and 1. For example, r could be rho plus 1 divided by 2, for example. Something between rho and 1. Now, again, since the limit of the nth root is rho and rho is less than r, we know that when n gets large, that the nth root of n is close to rho. In particular, if it's close to rho, it's going to be less than r. And that means the a sub n is less than r to the n. Get that by raising both sides to the nth power. And so that's really a comparison test. If the a sub n is less than r to the n, then comparison test, we are comparing this geometric series, which converges because the r is less than 1 and positive, and to this series. And since, again, the comparison goes the right way, the larger term series converges, we know that the a sub n converges. So even though we don't explicitly talk about the geometric series in comparison here, the root test and the ratio test really are just kind of backdoor ways to compare a series to a geometric series. In the divergence case, so now let's suppose that we have the limit as equals to infinity a sub n, nth root of a sub n being rho bigger than 1. Why does that imply divergence? And in fact, it implies really bad divergence. So if the limit as n equals infinity of nth root of a sub n is rho, which is bigger than 1, we can find a real number r between rho and 1. Again, as before, r could be taken to be 1 plus rho over 2 if you want. That'll be between those two numbers. Once again, if the limit of the nth root of a sub n is rho, then the a sub n's get close to rho, which means if they're close to rho, they're going to be bigger than r. Then if I raise both sides to the nth power, the nth root of a sub n is bigger than r, and remember, the r is bigger than 1. So this shows these a sub n's are really getting big, and it also gives us a comparison of the a sub n series to the geometric series r sub n, which diverges. So this is really another comparison test in disguise. And then here is the important part. And again, this is true for the ratio test also, but we're doing the root test because that's a little easier. But if we go back up to this statement up here, let me call it star right here, that if we now take the limit of both sides, we see the limit of the a sub n's is going to be bigger than the limit of the r sub n's. But again, if r is bigger than 1, you raise that such a number to a huge power, you get infinity. So that shows us that, in fact, the terms of the series are not even going to 0. The things we're adding up here are getting big. And so that we know that gives us divergence by the nth term divergence test. So we're going to use this fact, as we said later on, especially in our work with power series and Taylor series, that if a series diverges by the ratio test, then it really diverges because the terms you're adding up don't even go to 0. So here's a statement of that fact and how we'll use it. Okay, so what do we want to remember from this video? So if an infinite series diverges by the root test or the ratio test, then the terms of the series do not even go to 0. In fact, they're getting really big, and so that means the series will actually diverge by the nth term test. Now, you don't have to go through the nth term test. If you get rho bigger than 1 in the ratio or root test, you are done. You know the series diverges, But again, there's consequence that in fact the terms are getting big is going to be important in future work. And we discussed too that if you have a series whose terms are ratios of two polynomials p and q, we'll have you run through the ratio and root test for some problems like that. But in those cases, you're going to find rho equals 1. In other words, no information out of the test. So series like this, you're still going to have to be aware that you can use comparison tests, integral tests, or other types of tests. And then finally, the root test works really good, very well when you have exponential terms, things like 2 to the n to the n, etc. The ratio test is recommended, especially if you have factorials. So that completes our short discussion of the root test. So give these things some practice. Again, you can probably get through this course without knowing the root test, but it's nice to know because when a series can be analyzed using the root test, then that is usually a very, very quick and easy to apply test. So thanks for listening. We'll see you in the next video.